Hello guys, welcome to another discussion video. In this video we're going to discuss 2019 SDA paper 3 chemistry. So remember, don't forget to follow the page, and also we're trying to get to at least 1k followers and 10,000 likes. Okay, repost the video so that it can reach other students. So this SDA or combined science, this is like the core part of your triple science chemistry. So you can use this for revision even if you are doing triple sciences, okay, because this is the core part of it without the extended part. So you can use this material for revision. All right, question 1.7 says, which is going to be our question 1, of course, choose from the list a substance that fits the given description. Each substance may be used once, more than once, or not at all. Okay, so the substances we have there: ammonia, carbon monoxide, nitrogen, rubidium, chlorine, and lead. Okay, which substance is used as a reducing agent in the blast furnace? So that is going to be carbon monoxide. Okay, carbon monoxide. Okay, remember that in the blast furnace, you react your molten iron 3 oxide. Okay, you react it with this guy, carbon monoxide, to get the iron plus carbon dioxide. So this is the equation for this chemical, this reducing a reduction chemical reaction that happens in the blast furnace. Okay, and remember, definition of your reduction and oxidations is that you can use a definition based of the gaining and loss of oxygen. So in this scenario, you can analyze with both the gaining and the loss of oxygen. Okay, all right, let's continue. B says it's a gas produced from a catalytic converter. What does a catalytic converter do? Remember that a catalytic converter, basically you're going to get all your harmful gases, okay, your harmful gases, you put them through a catalytic converter, and then inside the catalytic converter, these gases are converted to less harmful gases, okay, less or gases that are not harmful to the environment. Okay, so here harmful gases include remnants or leftover hydrogen carbons that are left there. Okay, and then you can have carbon monoxide, and then you can have nitrogen oxides. Okay, we put an X there because you can have nitrogen monoxide, nitrogen dioxide, etc., etc. Now you, through inside the catalytic converter, you're going to change these harmful gases into less harmful gases like steam, H2O, carbon dioxide. Remember, carbon dioxide is naturally found in the atmosphere. Okay, so this is why you consider it to be less harmful. Okay, and then you can convert to nitrogen, and a very stable gas that we find in the atmosphere. So a gas produced from a catalytic converter from this, you can see that it's going to be nitrogen. Okay, it is going to be nitrogen. So remember, this is how the catalytic converter works. Okay, it converts harmful gases into less harmful gases. It's used for making nitric acid. It is used for making nitric acid. Now, nitric acid is made by reacting ammonia with oxygen. Okay, and then there are other processes that are involved there, but primarily is to oxidize your ammonia, and then eventually you hydrate it, and then you can have the nitric acid. Okay, you can get the nitric acid. Maybe let's just go over that with chemical equations so that we show what exactly is going to be happening. Okay, so you're going to take your ammonia, okay, you react it with atmospheric oxygen, or the just oxidize it, O2, and then you get nitrogen oxide. Okay, nitrogen oxide, which of course you're going to also continue oxidizing this in a chemical enclosure. Okay, and then you add more oxygen to this, you get your nitrogen dioxide. Okay, you get your nitrogen dioxide, and then this nitrogen dioxide you further you hydrate it, or you react it with water. Okay, you react it with water. Now when you react it with water, let's just say H2O here, and then essentially you'll get your nitric acid. Of course, this is the simplified steps on what is happening there, but just know that there is more behind the story of creating nitric acid. But essentially what you do is you react your ammonia with oxygen to produce what? Nitrogen monoxide, and then the nitrogen monoxide is further oxidized by reacting with more oxygen, and then you get nitrogen dioxide. And then this nitrogen dioxide is reacted with water, then you can get your nitric acid. Okay, so this is the simplified version of that process. Now let's go back to our question. So the answer here is going to be NH3 ammonia. Okay, ammonia. Of course, you should write the words the way they are given there, not the chemical symbols. D is in period 5 of the periodic table. So you go to your periodic table, and then you go to period 5. Now let's just go back down here, and then we'll go to the periodic table. Okay, so this is the periodic table. Remember that you have columns and rows. Now these rows here, these rows are going to be your periods, and then the columns are going to be your groups, group 1 all the way to group 8 there. Okay, so your periods run from period 1 to period 7. Okay, so period 1 is here where you find hydrogen and helium. So that is 1, and then 2, 3, 4, 5, and then we are in this bracket here. Okay, now from that list, remember we have this guy here. Okay, rubidium. Okay, we have rubidium. So that means, going back there, that means our answer is going to be rubidium. Okay, rubidium. Okay, now the only possible answers there would have been these 3 answers. Okay, nitrogen, lead, chlorine, and rubidium, because they're the only elements there, whereas these 2 here are what? Are compounds. Okay, they are compounds, but the only element that we find in group 5 in period 5 is going to be rubidium. Okay, it's going to be rubidium. Next question, E, reacts with water to form an alkaline solution. Reacts with water to form an alkaline solution. Now we know that according to our chemical properties of group 1 elements is that they react with what? They react with water to give a what? An alkaline solution. Okay, so if you react group 1 elements, even group 2, they will react with water to give what? An alkaline solution. Okay, solution plus of course hydrogen gas. All right, so for example, when you react sodium plus water, H2O, what do you get? You get sodium hydroxide plus hydrogen gas. Okay, plus hydrogen gas. Okay, so that means remember, rubidium is what is found in group 1. Okay, rubidium is found in group 1. So we can go back to the periodic table, so remember, this is group 1, this is group 1 right here, and then rubidium is found in group 1. So theoretically rubidium should follow the same reaction properties as these other guys like lithium, sodium, etc., etc. So that means the answer there is going to be rubidium. Okay, rubidium. Okay, so on to the next. Let's just remove this. on to the next question. It says equal volumes of water samples Wx and distilled water are tested for hardness before and after boiling using soap solution of the same concentration. The results are shown in the table 8.1. State two physical properties of water. Okay, physical properties of water is that it boils at 100 degrees Celsius, and then it melts at 0 degrees Celsius. Other properties include the density. The density of water is 1 grams per cubic centimeter. And then, so this will be the melting and the boiling point, and then this will be the density. And then we can also describe physically how you can interact with it. So you're talking about the taste, the odor, and the color. Okay, so it's odorless, tasteless, and colorless. Now those 3 points are just 1 point. Okay, so you can't say the first answer is tasteless, the second answer is odorless, etc, etc. No, you should, if you're going to mention the taste, the color, the other part, you should mention it as 1 point. Okay, tasteless, colorless, odorless. Okay, so it's just 1 point. All right, let's continue. State the type of B Roman figure 1. State the type of hardness found in sample X. Give a reason for your answer. Give a reason for your answer. Okay. Give a reason for your answer. Okay, the type of hardness that we find in sample X. So this is X here. What do we see? Before boiling, you needed 45 drops of the soap solution. Then after boiling, you needed less. Okay, you needed less. So the type of hardness is going to be temporary hardness in water. Okay, hardness in water. Okay. Now, what is temporary hardness in water? Essentially, hardness in water is the presence of magnesium, okay, or calcium ions, okay, in water. How to get? So basically, if you have a sample of water and it has high concentrations, or some concentrations of magnesium ions or calcium ions, then that water is deemed to be hard water. Okay, then you have 2 types of hardness in water. You have temporary hardness in water, and then you have permanent hardness in water. Now, temporary hardness in water is formed when you have calcium or magnesium hydrogen carbonate ions present. Okay, so if you have this guy, this compound here inside the water, and then for permanent hardness in water, it's whereby you have calcium or magnesium sulfate ions, or even chloride, calcium chloride in the water. Okay, now since we're dealing with temporary hardness in water, you can treat it by boiling, because when you boil water that is this guy here, when you have water that has calcium hydrogen carbonate, what is going to happen is that this substance is going to decompose to produce calcium carbonate, which can precipitate out of the water, therefore treating the temporary hardness in water. Okay, so let's give the reason first, and then we can look at the decomposition of calcium hydrogen carbonate. Now, what is going to be the reason for us saying that the water contains, or the water is temporary hardness, has temporary hardness in water, is because less drops of soap used after boiling, thus indicates water can let's just add hardness in water in. Hardness in water can be treated with boiling. Okay, so let's go over the answer one more time. So the reason we're saying that is temporary hardness in water is because after boiling we used what? Fewer drops of soap, indicating that you can actually treat the hardness in water by boiling the water. Okay, now what happens when you boil the water? Okay, so this is the chemistry behind that chemical reaction. Okay, when you boil water that has temporary hardness in water, it has this inside. Okay, so the water has calcium hydrogen carbonate. Okay, so when you heat this compound here, when you heat this, it's a soluble compound. Okay, it's soluble. So when you heat this, what's going to happen is that it will decompose. Decompose is when you have a larger substance that breaks down into smaller minor compounds or substances. Okay, so this will break down to form calcium carbonate plus carbon dioxide. Okay, now remember that calcium carbonate is insoluble in water. Okay, plus H2O, it's insoluble in water. So what happens is that this guy here will precipitate out of the solution. Okay, it will precipitate out of the solution. This is what you usually find around the element the kettle element. Okay, or whatever heating element that you have whenever you're boiling water. Okay, so this will be the scale that you find around that. Okay, so successfully you have removed the calcium out of the water. Remember what we said, by definition hardness in water is when you have this guy. Okay, when you have calcium ions or magnesium ions. Okay, now by precipitating out a compound that has the calcium out of the water, you have successfully treated hardness in water. Okay, Roman figure 2 says, suggest how the hardness in sample W can be removed. How can we remove in W? What is W? So W, let's go back to our diagram. So here in W, we can see that W, this type of hardness in water cannot be treated by what? By boiling. That means it's permanent hardness in water. Essentially what that means is that you have what? You have calcium or magnesium sulfate. Okay, so most of the time whenever we do examples we just refer to calcium sulfate. Okay, not calcium chloride or whatever. Okay, now this here cannot decompose. Okay, when you heat this water that has calcium sulfate, it cannot decompose. Okay, so calcium sulfate does not undergo decomposition. Okay, therefore you can't treat it by simply boiling. But what can you do? What can you do? What you can do is you can find another compound. Okay, you can find another compound that has a that has essentially a more reactive base here, a more reactive cation that will swap out with the calcium there. Okay, so something like sodium carbonate. Okay, which is going to be your soda. Okay, soda. Okay, so when you react washing soda with calcium sulfate, what's going to happen is that you're going to get a double displacement reaction. Okay, a double displacement reaction. So in the double displacement reaction here, you form calcium carbonate. Okay, plus sodium sulfate. What did I say about calcium carbonate? This guy always comes out as a precipitate. Okay, comes out as a precipitate as it's insoluble in water. Okay, so this will be the scum that you find whenever you're doing your laundry or you're bathing, and then you are bathing with the water that has what? Permanent hardness in water. So it will form that scum. Okay, it will form what? It will form the scum. So this is one method of removing permanent hardness in water. Okay, so what is the method called? The method is just called adding washing soda. Okay, so that's what we're going to do. Okay, add washing soda. All right, and then the other option is to do an ion exchange bed, okay, or resin bed. So essentially what you do is you make these beds, okay, in your water treatment plant. Okay, now these beds here, okay, these columns are going to be the way you have your ions, okay, your ions. So essentially you're going to look for ions that are more reactive than the calcium, looking at your reactivity series. So the most common one is going to be the sodium. Okay, so you're going to have these columns, okay, you're going to have these columns with activated sodium ions, okay, and then the water here will have calcium ions and the sulfate ions. Okay, now as the water passes through these columns here, okay, the sodium ions displaces what, the calcium ions, and then the calcium ions are exchanged for the sodium. That means the calcium ions will move out of the solution and into this column here, and then the sodium ions will get into the solution. So over time you'll see that when you look at a graph point of view, over time as the water passes these columns, okay, the sodium ions will increase in the solution. So this will be the sodium ions, and then the calcium ions, which are responsible for the hardness in water, will decrease. Okay, they will decrease in the water, therefore essentially treating the hardness in water. By definition, remember, hardness in water is the presence of this guy. We don't want this guy in the water, okay, or this guy in the water. We don't want these two ions in the water, as they are responsible for hardness in water. Okay, let's continue. Describe how the presence of carbon dioxide in the atmosphere contributes to the presence of hardness in water. Okay, so carbon dioxide will dissolve or will react. So first of all, the carbon dioxide is going to react with what? It's going to react with rainwater to form carbonic acid. Okay, weak carbonic acid. Now this carbonic acid is responsible for acid rain. Okay, acid rain. Okay, so that's the first thing that will happen. Okay, of course you are going to write this in words. Carbon dioxide reacts with water or rainwater to form carbonic acid, leading to acid rain. Okay, then the acid rain reacts with calcium, magnesium, mineral rocks. Okay, mineral rocks. So calcium, magnesium, mineral rocks include things like limestone. Okay, limestone, calcite, gypsum. Okay, so essentially from limestone it will be calcium carbonate. Okay, you know what happens when a carbonate reacts with what? Reacts with an acid. Okay, reacts with an acid, you form a salt. That salt is the one that is going to get incorporated into the water. Okay, and then it can cause hardness in water. And then from gypsum we do get sulfates. Okay, you get this guy here. Okay, you get sulfate. So you can you'll get something like this, calcium sulfate. And then from this you can create temporary hardness in water. But if you have this mineral interacting with the acid rain, then you get what? Permanent hardness in water. Okay, so this will be temporary hardness in water, and then those will give you permanent hardness in water. Okay, we can just give you examples here, e.g. Calcite. Let me just say calcite. All right, this reaction, okay, this reaction produces calcium, magnesium salts that are responsible for hardness in water. Okay, so that is the explanation. The first step is that the carbon dioxide reacts with the water to form carbonic acid. which is responsible for the acid rain, okay, which gives I meant to use this, which gives the acid rain. And then secondly, that acid rain reacts with what? With mineral rocks such as calcite, limestone, etc. And then this is where we get our what? This is where we're going to be getting our calcium or magnesium salts, okay, which are responsible for hardness in water. So you have to understand this from a chemical reaction standpoint of view, okay. So you need to understand the chemistry behind whatever process that you are trying to understand always, okay. Okay, let's just remove this. Okay, next question say draw a dot and cross diagram to show the bonding in water molecule. So remember the stick diagram for that is this, okay. So this can always help you whenever you're dealing with covalent compounds, okay. Just draw the stick diagram. Then whenever you have a single dash, that means a single bond, okay. Single bond means what? Single pair of electrons, okay. So the other element species, the other atom brings one electron, and then the other one brings another electron. And then a double bond, okay, so this will be a double bond. Then a double bond simply means you have what? Two pairs of shared electrons, okay, two pairs of shared electron. Then a triple bond means what? Three pairs of shared electrons, three pairs of shared electrons. So like that, okay. So you can always just draw these stick diagrams to try to orientate how you're going to be drawing essentially your structures, okay. So oxygen, it's 8, hydrogen is 1, so that means the electronic configuration for oxygen is going to be 2, 6, okay. Remember, the first shell houses a maximum of 2 electrons. The second shell houses a maximum of 8 electrons. So second shell, third, fourth, fifth, etc., house a maximum of 8 electrons, okay. So that means the first shell will get the 2, and then 8 minus 2, we are left with 6, and then that 6 goes to the second shell. And then as for hydrogen, the first shell will get 1 electron, okay. And then the electrons are finished. All right, so let's draw the structure. I'll start with the oxygen in the center, O, to acknowledge the nucleus, okay. So this is just us drawing the nucleus. So these are not the shells, no, this is essentially just the nucleus, okay. All right, and then if it's not mentioned in the question whether you're drawing the valence electrons, electron shells, or you're drawing all the shells, always draw all the shells, okay, to be on the safe side, okay. The first shell, 1, 2, so we're done with this. Then the second shell. Now the second shell, remember, we are going to create 2 single bonds, so that means we're going to remove 2 to be shared, okay. So we're left with what? With 4. 1, 2, 3, 4. All right, then we draw our hydrogen, H, to acknowledge the nucleus. Then the hydrogen only has 1, and then that 1 is going to be shared, so the 1 is here, and then dot. Now the dot is for the hydrogen, then the X is for the oxygen. So we do the same thing this side, X dot, and then H to acknowledge the nucleus, and then you're done. And then you're done. 9 says ethane, C2H6 and ethene, C2H4 are hydrocarbons. B, A, Roman figure I, state the name of the homologous series of which ethene belongs to. Okay, so ethene, alkene. Okay, so alkenes have a name ending of ene, okay, name ending of ene, hence alkenes, okay. And then alkanes, you have what? Alkanes, ane. All right. Roman figure 2 says state the name of the compound with 4 carbon atoms which belongs to the same homologous series as ethene. Okay, so 4 means but. Okay, but, and then same homologous series, ENE. So the answer is going to be butene. Okay, remember, 1 it's meth, 2 it's eth, 3 it's prop, 4 it's but, 5, etc., etc. All right. B says, draw the structural formula for ethane. Draw the structural formula of ethane. Now, ethane means what? Saturated hydrogen carbons here. So these are alkanes. That means they are only going to have single bonds. Okay, they are going to have single bonds. Okay, it means 2 carbons. Okay, it means 2 carbons. Oh, we are also given the molecular formula there. So C, how many carbons do we have? 2. Now everything is going to be single bond. Okay, and then our hydrogens. Then you just check. Remember, the number of hydrogens should reflect the ones that we have in the formula there. So 1, 2, 3, 4, 5, 6. Okay, and then carbon 1, 2. So C2H6. Okay. Now, another thing here, another trick here when it comes to hydrocarbons is that a carbon should have a maximum of 4 dashes pointed at it. Okay, what does that mean? It means this guy will have a maximum of 4 single bonds, and then a maximum of 2 double bonds, then a maximum of 2 double bonds and 2 single bonds. Okay, and then a maximum of, we don't really do triple bonds, but you know, when it comes to triple bonds, you'll have something like this here, or you'll have you'll have that. Okay, so these are the common configurations that you'll come across. Okay, so whenever you're drawing a carbon and then you count the number of dashes pointing at one carbon, you should only have a maximum of what? A maximum of 4 dashes. So 1, 2, 3, 4. 1, 2, 3, 4. All right. On to the next question. Describe a test that can be used to distinguish between ethane and alkane and ethene and alkene, and state the observation made. So the test is called the bromine water test. But essentially, you just bubble, or you react, or you mix whatever hydrogen carbon that you have with the bromine water. Okay, observation with ethane. So this is a saturated hydrocarbon. Okay, so that means it will not react with the bromine water, therefore the bromine water stays the same color. Okay, bromine water remains, okay, it does not change, remains orange brown. Okay, orange brown, that's the color of bromine water. And then with ethene, what's going to happen is that the bromine water will react with ethene. Okay, well, it will react in an addition reaction. Okay, so which is essentially a halogenation reaction. Okay, so that means when that happens, the bromine water will decolorize. Okay, so we just say bromine water decolorizes. So essentially it changes from orange brown to clear in color. Why does that happen? Okay, so remember, let's just start with the first one, the reaction between bromine water with ethane. Okay, so ethane is this here. Okay, so we have C H. Okay, so when you react to this, this is bromine is Br2. Okay, which is the same as Br. Br like this. Okay, so no reaction. So essentially what's happening here is that there's no space to add this bromine onto this structure here. There's no space, so they can't react because there's no space. Okay, this is why this reaction is not possible. All right. However, if you have a situation whereby you're looking at an ethene, which is not a saturated hydrocarbon, what you have with ethene is that it's a double bonded carbon. Okay, so you have something like this, and then you react with Br. Okay, Br. So what's going to happen is that this double bond will be converted to a single bond. Okay, when you convert that double bond into a single bond, what essentially happens is that you create an extra space. Okay, so I'm just gonna redraw this. Now we have removed what? The double bond. Now you do realize that we have created an extra space here. So this is where essentially this bromine can bond onto that structure. Okay, then the other one will come this side, bond onto that structure. Therefore this reaction is possible because you can essentially convert the double bond into a single bond, creating two new spaces there. Okay, creating two new spaces there. Okay, so let's continue. Ethane can be produced from ethene in the presence of a catalyst at around 180 degrees Celsius. Problem figure 1 state the name of the reaction that produces ethane from ethene. So the name of the chemical reaction that produces ethane from ethene is going to be what? Hydrogenation. Okay, hydrogenation, or the addition of hydrogen. Okay, the addition of hydrogen. Okay, so let's write down the chemical reaction. So I'm gonna use this diagram again. Okay, it helps to actually see what's happening when you use this type of setup. Okay, remember what I said, that whenever you have a double bond, you can convert this double bond into a what? Into a single bond, hence creating space. Okay, now H2 is the same as hydrogen, like that. Okay, then this is going to be like this: C, single bond, H, 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 H. So in the first step, we just converted this double bond into a single bond, creating what? Creating that extra space here. That extra space is where we're going to take this hydrogen, put it here, take the other hydrogen, put it there. Okay, so essentially this is going to be what? C2H6. So we moved from C2H4 to C2H6. Okay, this is ethene, and then this is ethane. Okay, so the addition of hydrogen to an alkene is called hydrogenation. Okay, the addition of hydrogen. Okay, so you can just add, you can write alternatively addition of hydrogen. Okay, addition reaction with hydrogen. And then Roman figure 2 says suggest a catalyst that can be used for this chemical process. So in this chemical reaction we use PT, platinum, or nickel. Okay, PT, so you need to write in full. Okay, platinum or nickel. Next, excess zinc metal is added to 200 cubic centimeters of 0.500 mole per cubic decimeter ethanoic acid to form zinc ethanoate and hydrogen gas. The equation for the reaction is shown. Calculate the number of moles in 200 cubic centimeters of 0.500 mole per cubic decimeter of ethanoic acid. Okay, let's remember our triangle. Okay, our triangle. what did I do now? Okay, so we have concentration here, moles, then here we have what? Volume. Okay, so what are we looking for? Moles. N is equals to concentration times volume, which is equals to, our concentration is 0.500 mole per cubic decimeter times. Now remember, this volume is in cubic centimeter, but we need it to match with the volume that is found there, unit volume of the concentration. Okay, so essentially we are to convert 200 cubic centimeters to cubic decimeter. Okay, and the way to do that is simply by dividing by 1000. Okay, 1000, and then this becomes cubic decimeter. This cancels that, the decimeter cancels the decimeter. Okay, that's 0. Yeah, then you just plug this into your calculator, and then you should get 0. You should get 0.1. Okay, 0.1. Okay, 0.100. So I'm gonna give my answers correct to three significant figures. Okay, 0.100 moles. So that's the answer. B, Roman figure 1 says calculate the number of moles of hydrogen gas H2 that are produced from the reaction. Okay, so here we're going to use ratios of reactions. Okay, ratios of reactions. Okay, so 2, so you're just going to take this as it is from the balanced chemical equations. Okay, COOH is 2, H2, then you take the coefficient, that is going to be our ratio, is to 1. So no number here means 1. Okay, so what does that mean? It means for every 2 moles of ethanoic acid, you're going to get 1 mole of the hydrogen gas. Okay, so that was the ratio means. Okay, then we have 0.100 is 2x. So 2x is equals to 0.1 divided by 2 divided by 2. X therefore is going to be equal to 0.05 moles. Okay, use your answer in B, Roman figure 1, to calculate the volume of hydrogen produced from the reaction at room temperature and pressure. Okay, so we know that this is going to be the formula. 1 mole of any gas at room temperature and pressure is 24 cubic decimeter. Okay, then for hydrogen we have 0.0500 moles is 2 unknown. Okay, and then x is equals to, we just multiply that, you should get 1.20 cubic decimeter. So this is just the cross multiplication. Okay, so 0.005 times 24, then you get this here. Remember your units. Okay, see Roman figure 1, a gas is produced when dilute ethanoic acid reacts with zinc. State one observation that will be made. If you are producing a gas, then the observation is going to be effervescence. Okay, or production of bubbles. Okay, bubbles. Roman figure 2, the experiment was repeated using dilute hydrochloric acid of the same concentration. State and explain the difference that will be made on the observation between the two reactions. Okay, so the difference we're going to see is that when you are using more bubbles are going to be produced when using HCl. Okay, HCl. The explanation is that HCl is a strong acid. Okay, strong acid that fully dissociate or fully ionizes in a solution. Okay, fully ionizes in a solution, while ethanoic acid partially ionizes in a solution. Now, one might wonder, what exactly are we talking about? It simply means that whenever you have HCl, okay, and then you make a solution of HCl, what is going to happen is that you'll have all of this hydrogen. Okay, this hydrogen is going to ionize to form hydrogen ions. These hydrogen ions are the ones that are responsible for, all the chemical reactions that acids undergo when they are reacting with other things. So that means the acid can go and attack what? Can go and attack the zinc. Okay, now if you have more of these hydrogen ions attacking the zinc, you're going to get what? More of the hydrogen gas. But if you have ethanoic acid, which partially dissociates or ionizes in a solution, that means if you have this guy here, COOH, okay, when you have this, what's going to happen? Some of the hydrogen will form hydrogen ions. Okay, However, the other part, or the other hydrogen, will remain in its molecular structure like this. Okay, so that means you have fewer of these hydrogen ions to go and react with the zinc, producing what? Less of the gas. So that's what it means to have full ionization and partial ionization. Okay, so you can think of it like full ionization is when you have 100 soldiers and then you are fighting 50 people, and then you release all of the soldiers. And then for partial ionization, let's say you have the same 100 soldiers. Now instead of releasing all of them, you like release 50% of them. Okay, so which one will win the battle first? The first one, because they are stronger, there's more of them. Okay, so essentially that's what it means. All right, thank you guys for listening. I'll see you on the next one.